Okay, so last time we talked about SN2, and so that's the one-step mechanism, trigonal bipyramidal geometry, inversion of configuration, and it's bimolecular, which is what the 2 stands for. But there's an inverse relationship. If it's SN2, it's one step, although I may complicate that today. If it's a SN1 mechanism, it's at least 2 steps. Okay. So the difference between SN1 and SN2 is that SN1 is kind of the mechanism that occurs if SN2 cannot. So if you end up with, let's say, a tertiary alkyl halide. So R stands for, you've probably seen R, but R stands for any alkyl group. So it's just a generic alkyl group. I have this alkyl halide. This is what kind of alkyl halide? Primary, secondary, tertiary? Tertiary? We all agree with that? We all know that? If we don't, I'm just going to keep asking that. You need to know that, particularly for these reactions. So, tertiary halide plus any kind of nucleophile. So I've been using hydroxide in the past. Hydroxide tries to attack the carbon with the chlorine. It can't because it's tertiary, it's too sterically hindered. That doesn't mean that substitution will not occur. It just means it's going to happen by a 2-step mechanism. So I'm going to break the carbon-chlorine bond, and I'm going to form my tertiary carbocation. Tertiary carbocations are stable, right? They're the most stable, or they're one of the most stable. And the reason that they're stable is because, remember, each alkyl group is pushing some delta minus charge into the carbon to make it closer to being neutral. Now, what we need to do is we need to write the transition state for this step. So the transition state is going to be the average of the reactants and the products. So I'm going to go ahead and, and the transition state also is where we make or break bonds. So if I am going to write the transition state for this, I'm going to write it like that. Bless you. So what's happening in this reaction? I'm breaking a carbon-chlorine bond. So what should go between the carbon and the chlorine in the transition state? A dashed or dotted line, indicating that there's a partial bond, because the bond is partially breaking in the transition state. Now, we have to average, so we average bonds. Bond, no bond. Average, partial bond. How about charges? Carbon 0, carbon +1, the carbon's charge is partial positive, which means delta positive. Chlorine, 0 minus 1, its partial charge, delta minus. Okay? So in the transition state, bless you, it is the average of the reactants and the products, but what we really should start doing is thinking about what's happening. And what's happening is I'm breaking a carbon-chlorine bond, and the electron density is being transferred from the carbon to the chlorine, which is going to leave the carbon positive and the chlorine negative. And why can that happen? Because that's a polar covalent bond. That would not happen if the two atoms had the same electronegativity. Okay. Right? Everybody okay with that? So that's step 1. And I forget, the first step is called the rate determining step. This is the slow step. And then in the second step, my hydroxide is going to donate its pair of electrons to the plus charge, to the carbon with the plus. So I'm using a full arrow to indicate the movement of both of the electrons from the oxygen. And so when I do that, I end up with my final product. I'm going to leave space for a transition state here. So my final product is going to have my tertiary carbon and then my OH. Can you write the transition state for this reaction? Tell me what I need. Dash line between the carbon and the OH. What else do I need? Where? So what on the C? And what on the oxygen? Okay. Now, people have asked, like, what is this? This is a double dagger. And the double dagger means that what's in the brackets is a transition state. Sometimes we put intermediates into the transition state. We might put them in a brackets, but the double dagger means it's a transition state. So when you see that, that's what it means. Right? So there's a complete mechanism, complete two-step mechanism for SN1, for this SN1 reaction. So I'm at some point, probably on Friday, going to give you a take-home quiz where you're going to have to write the mechanism of an SN2 as well as an SN1. Okay. And this is the basics. Okay. So that seems pretty easy. But let's talk about the types of nucleophiles I can do this reaction with. So I'm going to classify, and I did this at the end of class on Monday, but any nucleophile with a negative charge is going to be classified as a strong nucleophile. Now we are going to use what the quiz was on today for determining which nucleophile is stronger than another, but I'm going to classify anything with a negative charge as being a strong nucleophile, and that leaves the question of what's weak. Weak nucleophiles are those that are neutral. And the two examples of weak nucleophiles that we're going to use now are water and alcohol. And to be honest with you, water and alcohol are pretty much, in organic chemistry, they're very similar in how they react. Because one is HOH and the other one is ROH. So structurally, water and alcohols are pretty similar. Okay. So when I have this SN1 reaction, I don't necessarily have to do it with a strong nucleophile. I could do it with a weak nucleophile, like water. So let's go back and do this mechanism now of taking a tertiary halide, and let's go ahead and react it with H2O. And hopefully by the end of the period here, I will lay out how you're going to know whether a reaction is SN1 or SN2. But here's a reaction. I'm going to tell you this is an SN1 reaction. Of course, you probably should know that because tertiary halides can only undergo SN1. And I'm also going to change my definition of SN1 and SN2 and 1 and 2 here a little bit differently, because I'm going to say any one reaction involves a carbocation, and any two reaction, there's no carbocation. Because while we're doing SN1 and SN2, there's also going to be an E1 and an E2. And we're going to get to the E1 on Friday. And then on Monday, we're going to go over carbocation rearrangements. And then Wednesday will be review for the test. So I think I've already laid that out last night on Canvas. But if not, when I get back to my office, I'll check off to make sure everything's visible. So 1 involves a carbocation, a 2 mechanism does not. And that definition is going to help solve a lot of confusion that may happen. All right, so I've got a tertiary halide plus a weak nucleophile in water. What's the first step of my mechanism? It's going to be the same. Break the carbon-chlorine bond and form the carbocation. And when I ask you to do this, I'm going to ask you to write the transition state, but we already did write the transition state, so let's not waste time and do it again. Now, I have my water molecule. And with these kinds of mechanisms, the entire water molecule is going to add to the carbocation. I know what the temptation is. I'm going to say what the temptation is, but don't do it. The temptation is to say, oh, well, that's just going to break apart. Water just magically breaks apart into hydroxide and H+. And then you're sitting there going, well, yeah, that's what we learned in general chemistry, right? Because that's the equilibrium, and I even know what the K of that equilibrium is. Isn't it 10 to the minus It's 10 to the minus 14th? I hope so. Right? Because when we go through and we solve it, we get the concentration of OH minus is 10 to the minus 7th, and the concentration of H plus is 10 to the minus 7th. What's the magic about 7? That's neutral pH. And what's the highest pH you can get? 14. So water, that 14 scale is set by that K, and it's basically the autoionization equilibrium. You might, well, who cares? Well, we have to care about this. Because here's the thing. People love to break water apart into hydroxide. And then they say, oh, well, the the OH minus is going to add to the carbocation, and the reaction's over with. And then I have to say, well, how much hydroxide is in there? And then they don't remember general chemistry, so then we have to go back through. Now you would say, oh, there's 10 to the minus 7th molar of hydroxide in water. Is that a lot? No. Right? 10 to the minus 7th is not a lot. So in organic chemistry, we can't just break water apart. The entire water molecule is what's going to have to add to the carbocation. So I'm going to do that down here. So my H2O molecule with my 2 lone pairs on the oxygen, it's going to take one of those lone pairs and it's going to donate it to the carbocation to now form a CO bond. Like this. And we'll go back and draw the transition state down here below it. Bless you. So what's this missing? What's this structure missing? Not a partial charge. I'll accept charge, but not partial charge. It's missing what kind of charge? Go through and put the formal charges on each atom. Right, how many electrons they came with, how many they now own.
Negative charge on the oxygen.
Oh. You're close. What should be on the oxygen? A +1. So the formal charge on oxygen is +1. Why? Because oxygen has 6 electrons when it's neutral. It now owns 1, 2 outright. It owns half of the other 3 bonds. So it owns a grand total of 1, 2, 3, 4, 5. It came with 6. It owns 5. What happened? It lost 1. That gives it a +1 charge. Now, there's lots of laws in chemistry, like law of conservation of mass, right? You can't create or destroy mass. You can't create or destroy charge. So when you take a +1 species and add it to a neutral species, you better be +1 on the other side. And so where does the +1 go? It goes on the oxygen. Okay. Now that is called an oxonium ion. An oxonium ion is when the oxygen has the plus charge. The carbon, when it has a plus charge, we can either call a carbocation, which is what I prefer, or some people call it a carbonium ion. And so the carbonium, the oxonium ion, that terminology is similar. But I just use the carbocation. So we make an oxonium ion. And when we make the oxonium ion now, in order to make the final product, that oxygen wants to go back to being neutral. So how is it going to do that? It's going to break the OH bond. We're going to lose or form an H+, and then our final product, which is now going to have the oxygen having a completed octet, and now neutral, so we make, we make the OH, so we make the alcohol. And whether you put the H+ over here, say minus H+ over the arrow, you're going to see me do it both ways. Now that H plus is most likely going to combine with the Cl minus, so that the overall reaction is alkyl halide plus water makes alcohol and HCl. And if we did this reaction in any other solvent but water, we would actually probably see some HCl gas coming out of the reaction. But when it's in water, the HCl just dissolves and you end up with H plus and Cl minus. So that's a little bit more complicated, SN1, but that's how SN1s work with neutral nucleophiles. Notice it was 3 steps and not 2. And in being its 3-step mechanism, it's going to have a transition state, an intermediate, a transition state, and an intermediate, and then down to the final product. The first intermediate's the carbocation, the second intermediate's the oxonium ion. So intermediates are always surrounded by 2 transition states, because the intermediates are the valleys. So the other, the SN1 that we wrote before went through 1 transition state to the carbocation intermediate, and then a second transition state to the final product. So it only had 2 humps. This one has 3. So it's got 3 transition states because it's got 2 intermediates. And there may be those kinds of questions in the textbook. And I may ask them as well. Like I could give you a diagram and say, what kind of reaction is this? And sometimes there's more than one answer. Everybody still with me? Should probably ask a question to see if that's really the case. But let's look at the transition states now. So let's just do that on a separate sheet here. What would the transition state for this reaction look like? And again, if you're unsure, what's happening? What's happening is I'm forming a carbon-oxygen bond. So what kind of bond should go between the carbon and the oxygen? A partial bond, a dotted line. Okay, whenever you're making or breaking a bond, you've got to have a dotted line there in the transition state. Now, charges. What's the charge on the carbon? Partial positive? We all agree? I guess we all agree. I'm not seeing any real head nodding or anything like that. Thumbs up. Somebody in the afternoon always class gives me a thumbs up. At least they know they're listening. So we agreed, delta plus. How about the oxygen now? What's the charge on the oxygen going to be? Delta plus? Do we agree with that? Yes? I thought it was oxygen. It should be delta minus. You're still going to stick with your delta plus? Okay. You usually throw people off their answer. It is delta plus. Now, is there anybody going, why? Okay. Remember, it's the average of the charges. So oxygen here is neutral. Over here, it's delta plus. And so the average between those two charges is delta plus. In the past, it's been a negative going to 0. So think about what's happening in this transition state then. What's happening is the plus charge is being transferred from the carbon to the oxygen. Because what did the oxygen do? It gave its electrons to form the carbon-oxygen bond. And in the process, the oxygen basically lost ownership of an electron. Right? The carbon had none, the oxygen had 2. The oxygen shares its pair of electrons with the carbon, but if they now decide to split up, the carbon's going to take one of those electrons away from the oxygen, so in essence, it's lost ownership. So that's what's a little different about this. You've got an extra step, but you also, this reinforces the idea that when you're writing the transition state, take the average of the reactant and the product. And then think about what's happening. Before, the positive charge and the negative charge were reacting, there was no net charge at the end. But here there is. All right, how about the other transition state then? Of losing the H. So I'm going to take this pair of electrons and give it to the oxygen. And you do not know how many times over the next rest of the year that you're going to write that arrow in the wrong direction. I do, because I track those things, and that's the thing that people make the mistakes initially and like till the end of the year. They're constantly writing the arrow in the wrong direction. Remember, the arrow shows the movement of electrons, of negative charge. Negative charge always moves towards the positive. So that signifies that I'm breaking my oxygen-hydrogen bond. So I'm going to write a dotted line between the O and the H. Okay, so dotted line, what's being broken? Now, what about charges? What's the partial charge on the oxygen going to be? Partial positive. What's the charge on the hydrogen going to be? No.
Sarah, can you?
Partial positive.
Good. It's delta positive as well. I have to do this just to keep everybody on their toes. So yeah, they're both delta positive. Because again, what's happening? The positive charge on the oxygen is being transferred to the hydrogen that's going to become H plus. Okay. So there you go. So there's the transition state for those two steps. So again, if you're writing the transition state, the thing you want to do is write basically an average of the two molecules, but the dotted line always shows the bond that's being made or the bond that's being broken. And then take the average of the charges between the reactant and the product. And that'll get you the transition state. All right. So I also put in, I think I'd put in today's folder on Canvas a couple problem sets. And then before the problem sets, there's a little note of which problems you can do first. Like you can do SN1 and SN2 problems now, sort of. There might be some SN2s. There might be some SN2s that we need to talk about, which we will maybe on Friday, or we definitely will for lab next week, because we're going to do an SN2 reaction with an alcohol. And you have to write the mechanisms for that, but the video basically has the mechanism in it. You just have to follow the video. But we'll get to it we'll get to it. Maybe not by the time you do the lab next week, but we'll be pretty close. So what do I want to spend my last 5 minutes on? That saves you from having to look at your watch if I say 5 minutes. Here's what I want to talk about. So what do we know about alkyl halides? What reaction can a primary alkyl halide undergo? SN1, SN2, or both? SN2? So which one is it, SN1 or SN2? SN2? Only? Let's focus on SN1. What does an SN1 reaction have to have? A carbocation. So an alkyl halide can undergo SN1 if it can form a stable carbocation. Can a primary alkyl halide form a stable carbocation? No. Right? Rules of organic chemistry. And there's, I think, 3. There's, don't take it unless you have to. No 5 bonds to carbon. No primary carbocations. And I think that's as far as it goes. The student gave me a mug with just those 3 on it, and then a picture of me as Grumpy Cat. These are the things that you, over years, that teachers see. So I think she just had, I don't think there's a number 4 yet. And if there's 10, I sell t-shirts. So we're just at 3. No primary carbocations, no 5 bonds to carbon, and unfortunately you're stuck with the other one. So primary carbocation cannot form. So that means primaries can only undergo SN2. Secondaries. How about a secondary halide? SN1, SN2, or both? Both. So it can undergo SN1 and it can undergo SN2. Now, does that mean that there's total chaos and we don't know which one it's going to undergo? No. We'll refine that. Tertiary halide. What can it undergo? SN1 only? SN1 only? Yes. Why? Too sterically hindered to undergo SN2. So it can only undergo SN1. Now let me talk about nucleophiles for a minute. So if you have a negatively charged nucleophile, it can undergo SN1 and it can undergo SN2. Remember, nucleophiles are electron rich, and because it's a negative charge, it's the richest of the rich. I don't know if it's in the 1% or not, but it's got extra electron density, and it's got a full-blown negative charge, so it's rich. And it can give to either the carbocation, which is the poorest of the poor, but it could also give to a carbon with a delta plus, like a primary halide or a secondary halide. And so it can give to both types of mechanisms. It could directly attack and kick off the leaving group, and it can definitely add to a carbocation. Now, a neutral nucleophile can only undergo SN1 because it isn't that rich. Yeah, it's got some lone pairs, but it doesn't have a negative charge. And so it can only give to the poorest of the poor, which is the carbocation. So when we put those together, we can come up with a chart that says if you're primary and you react with a weak nucleophile, you get this reaction. If you're a primary and you react with a strong nucleophile, you get this reaction. And so that's what we need in order for you to be able to predict what reaction you're going to get. Okay? And if that wasn't in one of the videos for today or for Monday, I think it's in Friday's. So we'll stop here, but we'll generate this. We'll generate this table, and you can say, okay, do I have to memorize it? I guess, but you could also just learn the features, right? But there are some problems if you want to practice your mechanisms in the folder for today. The video is in the book and also in the folder for Friday. So we're going to talk about E1 mechanism on Friday. Okay. And there won't be a pre-class quiz